IIT Bombay. It is an honor for Parsec to host a talk by him. Thank you so much, sir, for accepting our invite. Professor Shankaranarayanan obtained his PhD from IUCA Pune. After his postdoctoral work at ICTP Trieste and Albert Einstein Institute in Germany, he was a Marie Curie Fellow at Institute of Cosmology and Gravitation at Portsmouth. Between 2009 and 2017, he was a faculty member at our institute, IISER-TVM. Then he joined the Department of Physics, IIT Bombay in July 2017. His research areas are black hole physics, early universe cosmology, modified gravity, and quantum gravity. Now I would request the professor to continue with the talk. Thank you, sir.
Nishal, can you see the slide?
Not yet, sir.
Sorry, can you see now? No. Hello?
Just a second, sir. Yeah.
Okay. So just for the sake of it, I will switch off my video. Is that okay? Just to be my video. Is that okay for this thing? My camera.
Yes, sir.
Because so you'll be able to. You are able to see it.
Yes, sir. We are able to see it.
Okay. Okay. I would like to thank Parsec team and Vinayak for inviting me to give a talk in the Astro Club of IISER-TVM. What I wanted to give is an overview of the status of cosmology and what are its achievements and what are the challenges that lie ahead in the like 2 decades or so. So I've used this the famous poem, The Six Blind Men and the Elephant analogy to drive what lies ahead of us. So many of you must have heard about this Six Blind Men and the Elephant, which is an old Indian story. And it was popularized in the West by John Sachs through his poem. So there are several versions of the story. However, all the version actually drives one thing which is kind of relevant for cosmology, which is basically the perception is subjective if you measure only part of it. So I will explain what does it mean by when I'm discussing this. But let us just look at the story itself, what the story actually is. So I'm just going to tell you one version of the story. So that I will spend a couple of minutes on the story because that will help us to understand where we are in with respect to cosmology. So there were 6 blind men in a village, and they've never seen an elephant, or they've never felt an elephant. So one day there were other villagers who tell that there is an elephant in the village. So then the 6 blind men said that, okay, let us just go and feel the elephant. So even though they cannot see it, they said, okay, let us just feel it. So what they did is they went, and then each of them went and investigated each part of the elephant. And then after they spent some time, and then they came back, and then they started exchanging notes about what they think this elephant is. So one person said that it is a wall, it's a giant wall. The other person said it's a rope. The third person said it's a fan, it's a big fan. And the fourth person said it's a sphere. The fifth person said it's a snake, and the sixth person said it's a tree. And then they started quarreling among themselves, saying that no, this is what is the elephant is. So then there was a sage who was going by, who heard this whole discussion among all these 6 people, and then he came and told them that each of you are right and each of you are wrong. That is because you have only seen a part of the elephant and you have not seen the full elephant. Now, to put this in the cosmological perspective, now we will replace elephant with universe and blind man with us and sage with observation. So the observations, each of these people are observing, or each of us are observing some part of the universe, which is the elephant, and it is telling us something about the universe. But we are actually only having, like how the blind men were about the elephant, they were only knowing some part of the elephant. We don't know a complete information about it. So to have a complete information, all these blind men have to talk to each other and try to see how to come up with a structure which is an elephant. Okay, so that is basically what the cosmology is currently is. So given this, let me now go the talk. So I have divided the talk into 3 parts. One is basically why the universe is supposed to be expanding and why the universe is finite. And once we understand that from observations, let us look at the theoretical framework, what it tells us about the universe and what are the predictions. And then in the final part, I will look at the challenges which lies ahead and how to describe the universe. So since it's online, many people cannot ask questions immediately. So what I would suggest is, if at the next interval I'll have a break, I'll take some questions that time. If there are something very pertinent questions which has to be answered, then I will take to the next question, so that then it will be easy for everybody also, so that there is some continuity as well. Fine. Okay. So let us just start. So to start, we will go back almost 200 years ago. So this is the question which was started by Olber, and it used to be referred to as Olber's paradox. I will call it as an Olber's paradox just for our own understanding in the next 5 to 10 minutes. So he asked this interesting question: why is the night sky dark? So everybody must have thought that it's a very stupid question to ask, but it turned out to be a very non-trivial question to answer. So we all have seen this daylight and in the night. But then the question which he basically made some assumption, and then based on this assumption, so he found that the night sky, if his assumptions are right, should be actually uniformly bright. And what he said is that possibly it could actually be even brighter than the daylight. So to go about understanding what his assumptions are, so let us just start with something simple. So let us understand 2 concepts, which is important, and then we will proceed with the rest of it. So let us consider light. Let us assume that we have 2 sets of light. Both the sets of light are actually of the same type. Everything, it emits the same amount of light. Let us take it. And so this one set of light is kept closer to us, other set of light is away from us. Fine. So now the light is emitting, the candle is emitting light. So it is emitting energy. And in astronomy and cosmology, we refer it to as luminosity, which is the energy which is emitted per unit time. That is, the candle is emitting X amount of photons, and that is like energy, and it is emitting X amount of photons at a given time. So this is what is referred to as luminosity. Now we also know that if we move the candle away, even though they have the same candle and they emit the same amount of light, for instance, on an average, then we know that that is dimmer than this. That is because the candle appears dimmer because it is far away from us. So this is, in astronomy literature or in the cosmology, it is referred to as flux, which is basically luminosity, which is the energy emitted per unit time, divided by 4 pi d squared, which is the surface area of the sphere. If d is the distance of the candle from the observer, then this is basically flux. So the flux is lower for the light for the candles which are away from us, while it is the flux of light which will reach us is much more than whatever which is closer to us. Hence, this we see it to be apparently brighter compared to this. So these are the 2 concepts which we will use to figure it out why Olber's paradox was a paradox for 100 years. Okay, so Olber made 2 assumptions. Please remember, Olber made this paradox in 1823. So when everybody thought that Newtonian theory of gravity is the correct theory of gravity, and the Newton's mechanics is the correct theory of describing motion. So Olber made 2 assumptions. One is that the universe is static, and the other one he assumed that it's infinite. So let us look at the consequences of this before we proceed with the analysis. So what does it mean by infinite? Basically, it means that we should be able to see any star at any direction, how far away it is, because it's infinite. Even if we assume that the speed of light is finite, since it is infinite, definitely any star we will be able to see at any given point of time. Now, the static implies that a distant star should have a similar brightness as sun, because it is only divided by 1 by d square. The d is the distance. So we know what is the luminosity of a sun. We'll assume that it is the same for all stars, and then we will get the we should be able to calculate the luminosity. Okay, so this is the assumption, and so based on this, these are the two consequences. So now let me just put a video, so we will to see how the night sky will actually look. Now this is a cartoon which I have taken it from Marinas. So the bright spot is basically sun, and depending on the other stars which we see at night, what we have done is basically, I'll just put the video again. So this is sun, and these are other stars, other galaxies it also could be, and we have just collected all the luminosities, assuming that the universe is not expanding, and let us just put it like this, and we are just superposed all this light, and this is what you should actually see. If you remove the sun, then what you should have actually seen in the night sky, if the universe was not expanding and it was infinite, what we should have seen is basically a bright uniform light everywhere. So it won't be night sky, it will actually be a bright sky. So, but we don't see this. Okay, so that is the reason why it was referred to as the Olber's paradox for almost 100 years. And once we have the theory of cosmology now, we know that it was why there was a problem. Okay, so now we have to revisit the Olber's assumption, and what we do is we will relax one assumption, and let us relax that assumption and then figure it out. What does it lead to? Fine. Okay. So let us wonder one thing which he made. Okay. So the assumption which he made is that the universe was static and is infinite. So let us do one thing. Let us just assume that remove the concept of staticity from universe. Let us assume that it is actually expanding. Why we want to have an expansion? Because we know that if the distances are increasing, then it is 1 by d squared, so the luminosity should decrease. So hence we are making an assumption that it is actually expanding. So which will imply that we will receive less light from distant stars. So now we will take a snapshot and we will reverse if it have been expanding, we will just reverse the whole how the universe is expanding. So instead of expansion, what we will do is we'll go back in time and let us look at how the universe is expanding. If it have been expanding, so earlier it would have been shorter in distance. Much earlier it would have been even more shorter. Even much earlier it would have been even more shorter. So then the whole universe, which if it have been expanding, it should actually be going back in time into a small region of space, and which is what we now refer to as Big Bang. So this is what would have happened. So let me just rephrase it again. If the universe was expanding, if you go back in time, then the distance between two stars or two galaxies would have been shorter. Much more previous time it would have been much more shorter. Even much more it would have been shorter. Then these would be going back, and everything would have been in a single point. So the two assumptions which basically Olber used, it was infinite and static, is actually cannot be true if you just take one assumption, which is that the universe is expanding. Then automatically the second assumption is also invalidated. So expansion automatically implies that the universe has to be finite. So this tells us something important. One is that if the universe is expanding, we will receive less light from distant stars. Now, the fact that the universe is finite, the distant light may not have reached us. So this automatically tells that the Olber's assumption of both staticity and finiteness has to be taken out of the context, and we have to think about the universe to be expanding. Otherwise, the original cartoon of this, this is what we should actually see. Since we don't see this, the only way we can explain it is to assume that the universe is actually expanding. The reason why we are taking expansion is because we want the light to be less, not more. Okay, so now what are the two consequences of this observation? First is that, as I mentioned, the luminosity should reduce. Luminosity or the flux will reduce. The flux is basically luminosity divided by 4 pi d square t. Since it is expansion, so d square is increasing, so automatically the flux will actually decrease. The second thing, which is interesting, which is where many of the observations we use, is what is called the Doppler effect, which implies that which corresponds to the change in the wavelength. So before I proceed with the Doppler effect, let's just look at what is the Doppler effect in sound. So the Doppler effect in sound is what we experience in day-to-day life, like a sound of an ambulance or a train. It refers to the shift of the frequency or the wavelength in the sound waves due to the relative motion between the source and the observer. So this we have done it in high school, which is basically the source. What we measure is basically the frequency of the which the observer receives is basically proportional to the frequency of the source times the velocity of sound divided by velocity of sound, speed of sound by speed of sound minus the speed of the source. So if the delta V is 0, then there is no shift. If the delta V is not 0, then automatically we'll see a shift in the frequency. Okay. So just to highlight what I mentioned, I've just given a cartoon here. If the source was stationary, then what will happen is that the sound waves will propagate isotropically at the same speed. That is called as the speed of sound as V sound. Then the distance or the wavelength between the two adjacent wavefronts will be, which is what we call it as wavelength, will be the same, and the frequency will be the same for all of them. Now, let us assume that the source is moving towards the right. So the same thing, what we will see is the right observer will see that the wavelength is shortened, while the observer on the left will see that the wavelength is increased, while the person on the top and the bottom will not see any change. So what it basically tells us is that the observer in the right will hear a higher frequency compared to the observer in the left, which is basically what I mentioned here. The delta V will correspond to the change in the frequency. And this is exactly analogous thing what we see it even in cosmology. So what happens is that, so let us now look at this picture. So if I had a galaxy who is at A, and this is what we actually measure here, we are here, the A is sending some light, and if there was no motion between A, and if there is no expansion, then whatever be the emission, we will be exactly seeing in the same spectra here as well. Let us take the case it is emitting at some frequency, and if you have an instrument here and which measures it, then we will be able to see exactly at the same frequency. Now, the reason why we know this is because we know precisely what are the hydrogen lines, and these hydrogen lines have been calculated to 15th decimal place by experiments, and we know what are the hydrogen spectra for different transitions, and using this we should be able to figure this out. Now, and this is what actually you see it from a nearby galaxy, in the sense, in the same, if there is a star emitting light, and you can figure it out what are the spectra for the nearby star, and you don't see any change. Now, if I take a snapshot of a galaxy which is very far, now what you see is that it should have actually been in this frequency, but since it is actually expanding, the frequency gets redshift. That's basically what you actually see, and that is what you see it as what is referred to as cosmological redshift. I'll explain this a little more in the next slide. So exactly in the same way as what we know from the Doppler effect in sound, there's the same analogous calculation which can be done, and it is called the cosmological redshift, which corresponds to the frequency of the light emitted from the light or from a distant star, which reduces due to the expansion. And it is given by the same expression like what we had. It's a new frequency of the emitted minus frequency observed divided by frequency observed, and which is what is referred to as Z, or what is called the redshift. So if Z is equal to 0, at Z is equal to 0, you will see that it is emission is equal to exactly the same as observed. That is what we see for the local galaxies. But if it is a galaxy is very far, we actually see that it is actually it is different. And this is because of the fact that we know that many of these hydrogen absorption lines, everything can be, we know it precisely from experiments, up to 15th or 16th different. Okay, so the concept of redshift comes in precisely from the fact that two things. So again, let's just go back to this. So the Olber paradox can only be explained if you had a universe which was expanding, and the universe expansion automatically implies that the universe is finite, it's not infinite. And if it is expansion, if there is a universe's expansion, then one of the important consequences that there is the change in the frequency of the light emitted and the light received are different, and that is what we call it as cosmological redshift. And this is what and the quantification tool is Z, which is the redshift. Okay, so now let's just look at what actually was observed. So this was Hubble in 1920. What he did was he was just looking at the spectra of several galaxies very far. In that case, it was megaparsec scale. We'll come back to it in the next slide. So he measured several of these galaxies, which are distant galaxies. And what he noticed is interesting. He noticed that the farther the galaxy from us, faster it was expanding away from us. So the speed in which the galaxy was residing was proportional to the distance in which it is distance away from us. So this is what he did. It took 10 years to take all these observations. So he took from 1918 to 1928 several observations of several of these galaxies. And this is the plot which I've shown here. This is the velocity, the left side plot, which is the velocity in kilometers per second and the distance in megaparsec. As many of you should know, what is megaparsec is? One parsec is 3.26 light years. Okay, so what he did is he just plotted the galaxy. So each of these points are galaxies in this Hubble plot, and this is the famous Hubble plot. So for each galaxy, he plotted the velocity and the distance. So as you can see, of course, his measurements were not very precise. It was a very scattered plot. But then he went again and said that let us assume that it is actually a linear fit. So he basically assumed he put a linear fit. So what he did is he basically said that the velocity in which the galaxies are going away is proportional to the distance, and this proportionality constant is now referred to as the Hubble constant. Okay, all the distances are measured in megaparsec. Now this is the recent data. Now there is even more larger data, but this I wanted to highlight it because of the fact that this is one of the paper, the Rees et al. Paper got the Nobel Prize in 2011. So I just thought that I will just highlight this here. So this is again the plot of velocity, again distance in megaparsec scale. Now please look at it that this is 70 years difference. So we have gone up to 500 megahertz. Now we are even able to go beyond one gigaparsec scale. So this is the plot. Now as you can see, the up to 300 megaparsec, it is almost like a linear fit. Now there are small deviations here and there, but still it is very good fit compared to what Hubble had when he plotted it. So now this is a very good fit, and this proportionality constant is actually very important, and this is one of the current problems in cosmology currently, which I will mention at the end of this talk. So there is a lot of effort which has been spent since 1920. People have been trying to figure it out, precisely measure this H0, which is the Hubble constant, and this is the evolution of time evolution of our understanding of Hubble constant. As you can see, earlier it was the measurement error margin was too high, and now it is still bad, but it is still good, but it is not very good as what we really want to have. And this tells you that how different observations are actually predicting different values. Okay, now why we are spending a lot of time to understand H0? Because this H0 gives you a rough estimate of the age of the universe, and the problem is that different observations predict slightly different values of Hubble constant. Hence, and this is what I mentioned, it is called the Hubble tension. Currently, everybody is trying to figure it out why the different observations, the local observations and the CMB observations seem to be differing a lot. So as you can see, this is 67.4, which is the Planck observation 2018. But this is what the Rees et al. Observations of 2018-2019 is. As you can see, this is 67.4 and this is 76.1. There's a huge discrepancy, and because of which the age of the universe this predicts and the age of the universe this predicts will be very different. Okay, so this is a current problem which I will mention at the end of the slide, and what people have been looking at it. So let's just okay, so this is the first part of the talk. So what I wanted to highlight is that just starting with Olber's paradox, we are able to figure it out that the universe has to be expanding. And given this expansion, we were able to make one precise prediction that it has to be the light which is received by the observer is not the same frequency as is from the receiver. We receive, sorry, let's just go back. We receive the emitted frequency and the observed frequency are different. They will not be the same, and which is basically what was seen by Hubble in 1920s. And we have been able to see this for different objects in the universe, and this is what we see. Okay, so this is the first part. Is there any question? If there is no question, I can proceed. Nihil? Hello? Yeah, sure. Right. That is all very, so there is always something called blind broadening. So let me just, okay, maybe I just mention it very briefly. So as you can see, when it emits, it will emit in one particular frequency, but there will be a broadening of light around that frequency. So it will not be a Dirac delta function. It will be like a Gaussian spread. And that Gaussian spread tells you that how what is the peculiar velocity, what is the peculiar motions of the objects around us. So, but the mean frequency, there will be a mean frequency in which we can figure it out. So there will be a mean frequency, and then there will be a line broadening. The line broadening is basically the local effect. Can I go ahead?
So there's a question in chat asking,
yes,
how do we know the emitted frequency of the star by observing it from the Earth?
Yes, so we never do that. So the thing is, so there is a lot of trial and error one has to do. So the thing is, what we know from theory is that the universe is made up of mostly hydrogen, and so that's what I mentioned. So the hydrogen is basically the main contribution to the universe. So, and we know, people have studied for the last 100 years different lines. So basically, there's something called Lyman frequency lines, Balmer lines, all those lines which you will study it in chemistry, which all has been studied, and they know every frequency possible. So what you know is that since it is emitting, and there will be an emission profile, and the emission profile will be shifted to that frequency. So like if it should have been here, this would have been the frequency it would have been emitted. But since it is not this frequency, but it has been redshifted, this whole thing will be shifted to a new frequency. So that is the first check. So you check this, and then you now look at other transitions. So you have to keep looking at all the possible transitions, which is what with the emission spectra is, or the absorption spectra is. And then you look at all those spectra and see whether everything should be coinciding with the same redshift. Not just one emission or one absorption we look at. We actually look at many emission lines and many absorption lines. And if all of them have the same, correspond to the same redshift, then we know what is the redshift of that object. So I just mentioned about one frequency, but to have a consistency check, we have to do it for at least for 4 or 5 frequency spectra, and then we will corroborate the data and then figure it out what should be the redshift.
Okay, sir. Thank you. So there's one more question in the chat. Why aren't the error bars equal in both directions for some data obtained? Yeah, it's in slide 20. Slide
20. Yeah, this is systematic errors, which I think we should not get into it right now. You're talking about this plot or the right plot or the left plot?
In the chat, it's just mentioned slide 20.
Okay, so there is a lot of systematics which goes into it. All these things, most of it I will not be able to know because all these are very collaborative work. So, but whatever they are given, we will just accept it because many of these things are a lot of work goes into it to figure it out what are the error margins. I will not be able to give you a precise answer, but there are a lot of systematics which has to be worried about. That's what I think. That is the only thing which you should take it. Okay, fine. So let's just now go ahead. I think there is a background noise I hear. If people can mute it, that will be of great help. Okay, fine. So now let us just proceed with the second part of the talk. So now what we have done is we have discussed some observational evidence of why the universe should expand and what are the consequences. So the consequences is the universe has a finite age, and then we should be able to measure it by using what we refer to as the redshift. Now, but this is not sufficient because we as physicists, we want to understand we have to have a fundamental understanding of the universe. So we need a mathematical formulation that can explain the expansion, and we also want to make predictions because we need a model, and the model will make a prediction, and then we can confront the model with observation. So now the first thing which tells you is that Hubble's law tells you that the universe is not static. Right? So that is what we actually kind of understood. Now, but then we want to now look at a theory. Now the theory, like Newton's electrostatics, Newton's gravity is a static theory, and it's described by one single scalar potential, Newtonian potential called phi. Okay. So now let us see how good is the Newton theory to describe our universe. So let us look at two galaxies, and let us assume that these galaxies are separated, our galaxy and some other galaxy, and the another galaxy is situated at 1 gigaparsec. The reason why I put 1 gigaparsec is roughly of redshift of 1. So let us now go back to Hubble's law. So the Hubble's law tells you that the velocity is nothing but h0. I have given the rough number as 70 kilometer per second. H0 is the value, rough current approximate value, and times the gigaparsec number which I put in. Now that comes out to be the order of 10 power 7 meter per second, which is like 0.2 times the speed of light. So of course we know that these particles which are moving are at very close to the speed of light. The Newton gravity is ill-suited, and we have to now come up with a new theory, and that is where the GR is, or the general theory of relativity is. So general theory of relativity replaces the time-independent Poisson equation into a set of 10 dynamical equations, which is what is referred to as the famous Einstein's equation. So you should treat it like analogous to Maxwell's equation, because in the case of electrostatics, we had a potential phi which was time independent, and if you want to look at the dynamics of the electric and magnetic field, then you have to come up with an equation which will be dynamical equation, and the Maxwell's equation is a dynamical equation because it has time dependence in this. So it's exactly the same way. So Newton's equations have to be modified with a theory which contains time dependence as well, and that is basically the Einstein's theory. So the left hand side of the Einstein's equation describes the space-time geometry, while the right side describes the whatever matter, rest of the matter in the universe, in the forms of all forms of energy and matter. So this is what we will take it now. So people have looked at solutions of these Einstein's equations, although they are these equations are partial differential equations. They are very complicated, but people have studied simple models. So many simple models of GR naturally predict and expand. So we will look at the standard model, which is what is called the Friedmann, Lemaître, Robertson, Walker. So the left side of the picture is Friedmann, and the right side is Lemaître. So they were the first to propose a model of the universe. So they made a simple assumption. The assumption is that the universe is homogeneous and isotropic. So homogeneity basically means that there is no preferred observer position. So anywhere in the universe, everybody is treated equally. So everybody has the same kind of physics, which is what it basically says. Isotropy is that it is same in all directions. Okay. Now, many of you might wonder that why this assumption is true. because when we see in the night sky, the universe is neither homogeneous nor isotropic. So this has been a puzzle for a long time. People have been worrying about it, and there have been experiments which have been conducted to test this hypothesis, this assumption. So this is the left side picture is basically the picture which I have taken it from Sloan Digital Sky Survey. So this is a 15 years of data which they have collected, and they are still collecting. So this is up to a redshift of 0.8. Now they even have a better value till up to 0.9 or 1. Now, since the position of the Sloan Digital Sky Survey is in the northern hemisphere, so they will not be able to see all parts of the sky. So that's where some parts of the sky is dark. So they don't have any data from them. They only have the data from these two sites of this in the sky. Okay, so that is for the SDSS sampling size. Now, this data contains a million galaxies. They have mapped more than million galaxies, and each galaxy is a pixel here, actually. Okay, so now, as you can see from here, there's one thing which is interesting to note is that in the largest possible scales, the universe is very homogeneous. Of course, there are sparse places here and there, but on an average, if you look at it, it's pretty nicely homogeneous and isotropic. So this assumption of homogeneity and isotropy, which is leading to an expanding universe, is not just for calculational brevity. It is actually because it seems to be that the universe in the largest possible scales is actually homogeneous and isotropic. So hence this is now referred to as the standard model of cosmology, and we will keep using this as a model to study to make predictions and then look at it. Okay, so what does the line element looks like? So the line element looks like something like this. If I would have assumed AT to be equal to 1, this is what we would see it in the special relativity as a Minkowski spacetime. So the only change is basically this A squared, which is what is called the expansion factor. So T is referred to as the cosmic time, because as observers, we are moving along with like any other observer in the universe. So this is the cosmic time, and the dx squared is the expanding 3 space. So this tells you that two adjacent points at any time will not be the same distance. It is going to keep moving as the time increases. If a of t is equal to 1, then the distance between the 2 points are going to remain the same. Okay, fine. So now the first thing is the FRW universe, the Friedmann-Robertson-Walker universe. It makes a prediction that the universe is expanding, and it automatically implies Hubble's law. We will not get into the details. If people want it, we can always discuss it at the end of this talk. But the first thing it tells you that since this A of t is automatically related to the Hubble parameter, H is equal to A dot by A. That is H0, which I call it as, which is equal to A dot by A, where A dot is the derivative of the scale factor with respect to time t. So now let us do the same thing. So let us now ask a question: what are the predictions now? So now one thing which is clear is that the FRW model it leads to Hubble's law. So that is the kinematic property. But we also want to know what are the dynamical properties and what are the predictions which we can have. So the first thing it will tell you is that as we go back in time, so as I mentioned in the previous time as well, the universe is going to be smaller and smaller. So what is the consequence for the universe when it becomes smaller and smaller? The first thing it's going to be is that the temperature of the universe is going to keep increasing as we go back in time. So and the temperature increase is going to be proportional to A of t, approximately proportional to A of t. There will be some changes depending on what we are using. So currently, if the temperature is, let us take 2.3 Kelvin, which is what we know. As we go back in time, the temperature is going to be scaled up by the factor. So what is the consequence of it? So this will have an interesting consequence. So as we go back in time, in the early times, very, very far back in time, the universe is actually very highly ionized. So basically, because it is too hot, or the temperature is too high, the electrons and protons cannot be combined into a hydrogen. So they will just be hit by. So let us take the case there is a photon which is coming here. The photon will hit the energetic photon will hit the electron, and it will become. So this will become ionized. So this will just be a ionized hydrogen or the proton. So this is going to happen continuously. So in the early universe, because of the fact that the temperature is going to keep increasing as we go back in time, so the universe is going to be highly ionized, and the electrons are not bound to atoms. The electrons are all going to be kicked out of the atoms because of the fact that there is high energetic photons which are going to be present because of the temperature is high, and the energetic photons will kick the electrons out of the atom, and all the atoms will be highly ionized. So the early universe is highly ionized universe, and of course the radiation and matter are highly coupled, and the energy keeps transferring. So the matter transfers energy to the atoms, transfers energy to the radiation, and radiation transfers to the matter, and this keeps happening continuously. So now let us not go back in time. Let us now start from early universe, and then now come back to our current time. So now when it was very hot, when the universe is expanding, so it's going to be the opposite is going to happen. The universe is now going to expand and it is cool down. Now as it cools down, what is going to happen is that the electron and now the proton will now combine, and it forms neutral hydrogen. Similarly, it forms other light elements like helium, lithium, and other light elements. Okay, so now this is where the last year's Nobel Prize for Peebles was given. So what they did was, this was the paper in 1965, and this is with Zwicky, the Dickey, and Peebles. So what they did was, I will also come back to this slide again later on for the CMB experiment. So what they did is the following. So they calculated, assuming that if you know what is the temperature at some time t, or that is at the current time t. So what they did is they went back and asked the question, what should be the temperature at different epochs in the universe, and they plotted. This was a 1965 paper. They plotted it for how the radiation will evolve, how the matter will evolve at different times in the universe. And then they predicted, they made some certain predictions of what should be the temperature at this time, and what should be the temperature at this time after a few seconds after the Big Bang. And they actually did that. And this is the famous plot. So if you remember, I want to point out that they said possible thermal history of the universe. They never said this is the history of the universe, because in 1965, they didn't know whether their analysis is actually going to be true. Now we actually say that this is the history of the universe. But that time they were very careful, and they said that they just call it as a possible thermal history of the universe. Okay, so fine. So this is the prediction, and for which the Nobel Prize was awarded to the Peebles last year. So what they said that is that as we go back in time, the universe is ionized. But then now when we return the clock, when we come back in the future, the universe is going to be cooled down. And what happens? What are the features it's going to happen? So once it cools down, now let us take the case that what happened here is that there was high energetic photon, and this photon was kicking the electron out of the hydrogen atom. Now when the temperature goes down, now this photon doesn't have that much energy, and the photon will not be able to interact, will not do anything to the hydrogen atom or to any other atom. So what will happen is that these photons will decouple, and they will propagate freely as photons without doing anything. And then this is what we keep collecting. So this surface is what is referred to as the last scattering surface. So this surface is when the photon or the radiation and the matter decouple. Until this point, they were interacting with each other. The photons were hitting the electrons, and then all kinds of reactions are happening. Thomson scattering was happening, Compton scattering was happening. All kinds of reactions are happening. After this point, the photons they will not be able to interact with baryons, what they call it as atoms. So they freely stream, and we receive these photons, and this is what is referred to as the cosmic microwave background photons. So I compressed a lot, but the thing is that as we go back in time, the temperature was high. So let us now reverse the clock. Let's come back in the original as the universe has evolved. So as the universe expands, the temperature cools down, and then there is an event which is what is referred to as the last scattering surface, when the electrons, atoms, and photons decouple, and the photons now just freely pass through, and they will reach us, and that is what we call it as a cosmic microwave background of photons. So why these photons are interesting? Because they give us a lot of information about the universe. So the first thing is that this was the prediction, and so this is what is the plot. So in 1964, Penzias and Wilson, they are radio engineers. So they were just constructing a radio antenna, and they were just they were measuring several signals, and they found an excess antenna temperature of 3.5 plus or minus 1 Kelvin, and they were not able to explain it. And this was exactly the same time when Decay et al., which is Peebles, they were trying to formulate the universe using the Friedmann-Robertson-Walker model, and they were and this excess temperature they were not able to explain. And this curve, which is basically the curve of Penzias-Wilson, which is they got a one number here. So this is the curve is a Kobe curve, which is measured by Kobe later, which I'll come back to the next slide. Now in this slide, so this is the Penzias-Wilson measurement which they did it. This is where they measured it in this frequency, close to 8 gigahertz, and this is where they measured, and they found the temperature to be of this with a large error margin, but that is not a, at the time it was still okay. And what Decay was mentioning is that they were able to get a curve, and their curve was basically from their analysis for this thing, and they showed that this has to be a black body spectrum, and they showed that if it is a black body spectrum of with a peak around 1.7 millimeter, then this should have a precise temperature which is consistent with what Penzias and Wilson measured. And this turns out to be the first evidence of Big Bang, because till that point there was no real evidence. Whatever I mentioned, it is all theory, and we will still didn't know whether this was actually true. So Penzias and Wilson showed that, measured this, and it was confirmed by Dickey's calculation that if this was indeed consistent with FRW universe, or the Friedmann-Robertson-Walker universe, then this has to be exactly this number, and they measured it around 9 gigahertz, and it was basically consistent with whatever they had. And for this, Penzias and Wilson got the Nobel Prize in 1978. So as I mentioned earlier, so the Decay could explain this model from FRW, and this turned out to be the first evidence of Big Bang. So in 1960s, there were other models. One is a Friedmann-Robertson-Walker model, and then there were other models as well. And all the other models are knocked down, and finally, it was only this model finally turned out to be the correct model description of the universe. Now, this is not the whole story. So the Decay et al. Also proposed that the spectrum, which we will see, that the black bodies, the CMB spectrum, the cosmic microwave background, should have precisely a black body spectrum. Okay. So now in the next slide, I'll just show you this picture. So this is basically from a Kobe measurement, and these are all the data points which they got, and with error bars. These are all with error bars. Now, as you can see, this is a perfect black body spectrum, which fits a perfect black body with corresponding to 2.725 Kelvin. Okay, so this is again by Kobe. Kobe just not measured this, but it also measured the first fluctuations, which I will show it in the next few slides. So, and Mather and Smoot got the Nobel Prize in 2006 for this. Fine. So there is a lot of evidence from observation which tells that the Friedmann-Robertson-Walker model, what is now referred to as the standard model of cosmology, is a very good model, and it fits the observations, especially the ones which we have mentioned about Kobe, which tells you that the black body spectrum, and what I mentioned about Penzias and Wilson, which is basically telling you that there is an excess antenna temperature of 3.5 Kelvin. Okay, so then there is a lot of effort has gone in to understand more about the cosmic microwave background. So the cosmic microwave background, since it doesn't have any other interaction, it is a freely streaming photon. So as it leaves the last scattering surface, whatever happens whatever has happened in the last scattering surface, it will gather that information, and of course it will be redshifted photons. But whatever happens in between the universe, in the sense, if something happens, if there is galaxies are formed or galaxies are merged, whatever happens, these photons will actually pass through them, and they will also gather that information. So as an observer, we can actually gather we can take by looking at this cosmic microwave background observation, we should be able to take a snapshot of the universe up to a very large distance for a very far away in time. Okay, this happens to be at a redshift of 1,500 approximately. So, sorry, 1,100. So it happens to be around 1,100 large scattering surface, and we should be able to know precisely everything, or to a reasonable extent, we should be able to know whatever has happened at least till last scattering. So the details are the following. So it basically, it tells us from the last scattering surface, it will tell us, we can extract a lot of information like what were the initial structures, or what were the initial density perturbations, and what are the other features which happened during the epoch. Okay, so this is what is now, I will not get into the details because it will be more technical. So what FRW model predicts is that there will be a density perturbation. Given a density perturbation, what will be the density perturbation is, and how these density perturbation propagates, and how these galaxies are formed. And those initial density perturbations are seen in the CMB observations, and this is what the Kobe saw. And if you can see the WMAP, now Planck is even better. So the WMAP can actually measure it much more precisely. Okay, so this is all the good things about cosmology, about the model. The model has 6 parameters. For people who are not worried about it, but we can just say that these are independent parameters. By looking at the different spectra, we should be able to precisely fix at least part of it. Most of this can be precisely fixed. Okay, so now this, so the first thing is that it can, the model can fix all these things very well, but it comes with a, although it is successful, but it comes with a price. The price is that, now this is the bar chart which we have about the universe. What we understand is that if this has to fit all these observations, then only thing is that only 5% of the matter makes up the universe. That is the matter which we see, that, or the baryons, what we call it as baryons, the atom and the photons. They only make up to close to 5%. Rest 95% is made up of objects or matter or the energy which we have no information about. So out of this 95%, 25% is what is called as dark matter, and the rest 69% is what is referred to as dark energy. Okay, but the worrying problem is that although this can actually, the model can explain it, but we have no fundamental understanding of what is dark matter and what is dark energy. So in the rest 20 minutes or so, I will discuss what is dark matter and what is dark energy, and how do we know it and it exists, and what are the things people are doing. So I can take a break here, and so that I can take questions, and then I will proceed with the challenges in cosmology. Nihil? Hello?
Hello, yeah.
Yes. If there is any question, then I can take it.
There's a question. Shouldn't the surface of the last scattering depend on the frequency of the photon?
No. No, I don't know whether I understood the question then. So given this that we have we know what is the frequency of the photon in the current, we measure them, right? Because we know that it is a black body spectrum, and we know what is the temperature at this frequency and what is the frequency at this. As I mentioned in the Kobe, so we know that we know precisely what is the frequency, and we can fit it. Now, and we know that it is a black body temperature at 2.75. That is the peak depth, right? Now I can go back and I can use the Friedmann Robertson Walker, and I can measure exactly what temperature it is. So basically, this is nothing to do. The surface is just a surface for our own understanding. what it basically tells you is that what is the temperature in which the photons and the baryons decouple. Basically, they don't stop interacting. They will still interact very weakly, but they will not interact strongly. So that number we can precisely know from the temperature, because the temperature is fixed by the physics, because that is all we know, because we know what is the hydrogen ionization energy, all those things we know. So in that sense, we can precisely know what is the temperature is. Once I know the temperature, I know precisely what should be the redshift of it, in material of whatever be the frequency. So the frequency is basically tells us, this black body spectrum will tell me what is the temperature is. So once I know what is the temperature is, and I know what is to be the temperature of the ionization of decoupling of photons and baryons, and so that will fix me exactly when should be this last characteristic surface should occur with respect to the redshift. So the physical quantity is the temperature, but the easier thing to understand is the redshift. But the actual physical thing is the temperature.
Okay, sir. So there's another question. How is the composition of universe with respect to dark matter and dark energy determined?
That I'm going to do it in the next few slides. I will mention this in the next few slides.
Okay, sir.
Can I proceed?
Yeah.
Okay. So now I have told all the good things about cosmology, standard model of cosmology. So now there are lots of challenges, as I mentioned earlier. The first thing is that we still have a universe in which 25% is dark matter and 69% is dark energy. These numbers keep changing, but I will just keep these numbers as 69-25 for the present. But we keep changing depending on what the how precise the observations become. So we have to know what do we do with it. So we have no information about them. So what are the things which we have to learn about? So this is where the challenges come in. So this again will go back to this cartoon. So I have now replaced everything. So this is the observations we are telling. So now some people say it's dark energy, some people say it's dark matter, some people say it is dark matter is because of supersymmetry, loop-bound gravity, modified gravity. Some people say it's string theory because the early universe should be described as string theory. So these are the challenges which we have. So all of them are, as the sage mentioned, everything. It seems to fit certain things, but it doesn't seem to fit everything. Okay. So let us now look at two aspects of it. Let us now concentrate, because that is 95%. So what is dark matter and what is dark energy, and what are the alternatives to it? Okay. So what is dark matter and how do we know that dark matter is there? Okay. So the first thing is that the proposal is that the dark matter neither emits nor absorbs any detectable amount of light. So basically there is no interaction between light, between electromagnetic light with dark matter. So they don't interact. So how do we know dark matter exists? Of course it has a mass, or it has energy. And of course, all objects which has energy will interact with gravity, and that is what GR tells. So they interact with they interact via gravity. So how do we know this? This we know it for the last 80 years or so. So people measured the rotation curves of the galaxy. So what they did is they just they know what is the rotation speed of various stars around the galaxy. For instance, our own galaxy, we can for our galaxy it will become a little difficult, but we can always do this, and we can calculate what is the rotational speed of various objects as a function of distance. Fine, and so this is from the distance from the center in light years. This is calculated. Now you can calculate what is the velocity of it. How do we calculate the velocity? Because we know that what should be the mass. We know what should be the mass enclosed within that galaxy, within that region of the galaxy from the distance, and divided by r. And this is what we know from Newtonian theory. So you calculate. Now, if I know what should be the galaxy, and then we measure it, and then this is the calculated. If I assume that there is no dark matter, or there is no something called dark matter, and if we just assume that it is should be there, we know that we don't see a galaxy light beyond certain point, beyond certain distance. So hence there is no mass. So since the mass is saturated, so then v squared, which is basically the rotation speed, also saturates or it goes down and finally it will become 0. But we don't see that happening. What we actually see is that this keeps expanding for a larger and larger distance, even though the galaxy, as a visible galaxy, it stops after some point because we don't see stars beyond the point. So this was the first instance where the galaxy was, the dark matter concept was proposed. Of course, people were not sure about it at that time, but now the concept of dark matter is there. So basically, the dark matter was added to explain this is the calculated from simple Newtonian mechanics, and this is the measured. And if you want to see that this has to be matching with this, the only way is you have to keep adding mass, because that is the only way we can actually fix it. Why do we think the Newtonian mechanics is true? Because these are all very small. The gravity is not very strong, so we can actually calculate it, and it is Kepler's laws of motion are all very well. They all can be measured well, and you know that it can be precisely. It gives the correct prediction. Fine. So given this, we can ask the following question: if this has to match, the calculated thing has to match with measured, the only way is we have to keep adding mass to it. And this mass we don't see in the universe. So that is where it was called the dark mass, because of dark matter, because we don't see them. And if they would have interacted, we would have definitely seen them. If they interacted with light, definitely we would have seen them. So since they don't interact with light, hence we don't see them. So what are the properties of dark matter? We know. These are the only things we know about dark matter. We don't know anything beyond whatever I've listed here. So they should have remained stable at least for lifetime of the universe. So that's where I've called it as 10 power 14 years. They should be feeble couplings to other matter except for gravity, because they have to interact with gravity because it has energy. But it cannot interact with radiation, or it cannot interact with hydrogen atom, or it cannot interact with electrons. So there is no way they can interact. Should have been produced in large numbers, because otherwise, how can these can be present in most of the galaxies? So it has to be present in large numbers. Now, this is what I will mention in the next. This will be able to. It should be able to possibly to see the structure in the universe consistent with observation today. I'll come back to this in a minute. So, of course, a lot of theories have been floating around. It could be something called an axion, which is still, before it was popular, suddenly it went down, now suddenly it has become popular. Something called weakly interacting massive particles, which is also now again popular. Neutrinos have been there for a long time, but we don't know anything about it. So the only thing which I mentioned is these are the 4 properties which should be there, and only these 4 properties we know about it. So with these 4 properties, people have been trying to see what else we can measure and see precisely that there is a dark matter particle. So we don't know anything about it. There has been a lot of things about, a lot of experiments have been conducted to figure it out, the dark matter, what kind of dark matter properties are, but we still are not there anywhere. Okay. So one thing which we know about dark matter is that if this dark matter should be present, because they will be responsible for the structure of the universe. How do we know this? Okay, so now let us take, we have 2 electrons, and we have a proton, and there is another proton. And since there should be, the universe is charge neutral, so if there is a charge, if there is a proton present, or if there is a positive charge present, then there will be electrons which will be going around it. Now, if there is a proton and there is another proton which is there, then these 2 protons will be screened by electrons, and the potential and the Coulomb energy potential is no more E by R, but it will also have a damping factor, which is an exponential of e power minus k0. K0 is some damping strength, so it will not be there. So it will actually be very damped, and we know that the universe was highly ionized because of the fact that there was a constant interaction between radiation and matter or the hydrogen atom. So they will. So the thing is, if any interaction happens, that the Coulomb interaction would have been highly screened. It cannot have happened just by Coulomb interaction. Fine. So I will. So the next step is, so now since dark matter doesn't interact with light, so they cannot be screened. So the only way they could have been, they can dominate. So if they dominated the universe, for instance, then what they will do is they will be acting as an effective seed for structure formation. So let us just take the case. So we know that the universe, currently we have galaxies, we have stars, we have galaxies, we have superclusters, we have lots of structures in the universe. So these should start with a seed field, which is what is called the seed perturbation, and then these since gravity keeps attracting, they should keep forming. Now, if there was only baryons and electrons, then they will not be able to screen it, even though they have gravity, but their potential energy the Coulomb energy is very strong. So hence, they will be suppressed by the Coulomb screening. So then they will not be able to see it. So, but since dark matter don't interact with light, or they don't have interaction with electrons, so they will be able to dominate it. So this is a picture taken it from the Chicago group. So what they have done is that they started a simulation where there are dark matters, and then they just evolved them for from z is equal to 28, and they evolved it till now. And this is a snapshot, assuming that there is dark matter in the universe. Now they will. So if there was no dark matter, you will not be able to see structures like what we see. So this is like a structure which we will see in the universe currently. If we were here, we will see that scattered through galaxies are scattered, stars are scattered everywhere. So so there are two reasons why there is dark matter. Evidence of dark matter is present. We know that there is evidence that the dark matter is present in the universe. One is the rotation velocity of the stars, the galaxy. And that precisely tells you that there should be some other mass which should be able to jack up that velocity. The second thing is, if there were only baryons and there were no dark matter, then we will not be able to form these large-scale structures because of the fact that these are all screened. They will not be able to. You will not be able to see with this screening. They will not be able to do anything. Okay, fine. So now let us now go to the next part, which is the dark energy. So if you think that dark matter itself was strange, dark energy is even more strange. Okay, so to go back to this, we'll just take a container of a gas, which we all know from our school days. So how do we know that there is a pressure? We know that these gas particles collide with the walls of the container, and this creates the pressure. And we know that if we keep putting more and more particles, the number of collisions will increase and the pressure also increase. So this is all what we know for the normal matter which we experience in day-to-day life. But the dark energy is strange because the pressure of the dark energy is negative. Okay. So if you increase the number of dark energy molecules, then automatically the pressure decreases, which is opposite to what we know from the gases. Because we know in the gas, if I increase the number of particles here, they will collide among themselves. They will also collide with the walls of the container. So the pressure will increase. Now, if we, in this case, when I increase the number of particles, dark energy molecules, the pressure decreases. Now that is one peculiar feature. Now the other peculiar feature is that in the case of matter, the dark energy, in the case of matter, we know that it is proportional to it is not proportional to the volume. However, in the case of dark energy, the energy is equal to proportional to the volume of the empty space. So as the universe expands, the dark energy also the energy of the dark energy also keeps increasing. So how do we know that this is true? This is again from the fact. This is the Nobel Prize winning work of Rees et al. 1999. So this is a plot of luminosity distance. This is redshift. So what they did is that they looked at supernova at different redshift, and then they looked at the luminosity, and then they calculated by a lot of analysis had to be done, and then they precisely plotted the luminosity as a function of Z as a redshift. Now what they found is that only if so the green light is the green text is not coming out well. So what they found is that if this has to fit the data, the supernova data up to redshift of 1.5, then you need to have a component like a dark energy, which should be 69% of the universe should be present. The rest, matter plus baryon, should be 31%. And radiation. Unless otherwise you fit this, it will not give you the correct data fitting. So this is also true with the CMB observations. I have not given the observations here, but even with the CMB also gives you a roughly the similar number. So there is a small changes here and there because of the systematic, but otherwise it gives you the sum, roughly the same. So what the dark energy does is that what they do is they accelerate these particles at the largest possible scales in the universe. So basically, while the gravity tends to bring all the particles, all the stars and the galaxies together, this dark energy tries to separate them out. So that is where the universe starts accelerating. So that is why we call the current epoch of the universe, which is currently we are experiencing, it's an accelerated phase. While in the earlier phase, like around z is equal to 100, for instance, to z is equal to 2, we have been in a decelerating phase. Okay. So now, so the thing is, so the other possibility, which is what people have been working on, is that possibly we don't know GR or the gravity itself correct. Maybe we are making a mistake. We are having a wrong theory of gravity. Since we don't measure dark energy directly, we only measure it from the Hubble diagram. So the possibility is that if you modify gravity and this modification can mimic exactly like dark energy, when will it give you? So this is something which we have been working on as well. So your Einstein's equation is not exactly true in the largest possible scales. It could be true. So there are several modifications which people have been looking at. So what people have been able to show to some extent is that they will be able to mimic, if you modify gravity at the largest possible scale, they will also be able to mimic exactly like a dark energy, but they will have other features which can be possible to distinguish in the future observations. So this is still in progress, but people are actually looking at it. So now let me come back to what I mentioned, which is the current, what is called the crisis in cosmology, people call it, but I just call it as a H0 tension. So as I mentioned, so people, one of the crucial features is that the Hubble parameter has to be determined, because that fixes a lot of parameters, a lot of things in the universe, because it fixes the age of the universe and it will tell you at what epoch the last scale structure the universe happened, the last scattering surface happened, and what epoch certain other events happened in the universe. So measuring the H0 is very important to understand, to have a fundamental understanding of the universe. So people measure H0 by various measurements. Planck also gives you the value of H0. The supernova measurements, as I mentioned, the Rees et al. Also gives you this thing. Now, currently there is another third alternative, which is basically the gravitational wave observation. Also gives you a way to measure an independent measure of measuring H0. Okay. Now, this is the plot of this is a diagram of several observations which people have measured, and these are all basically large distances like CMB and things, which are because we are measuring from z is equal to 1000, and these are basically from different observations. Okay, so let us just go here. So this is Planck, and this is Shoes is another observation, which is local observation. Holikov is another local observation. So these are all different observations people are measuring. They are all seem to be deviating from each other. Now the problem is that the gravitational wave observation, which is an independent observation, it seems to be sitting exactly at the center of the supernova observation and the CMB observation. So it is not very clear whether how to resolve this, what is called the resolving the H0 tension. People have been worrying that maybe there are observational errors, which people have been trying to figure it out. People think that maybe neutrinos are self-interacting. Maybe that is not, we don't know anything about it. People have been trying to find extensions to lambda CDM model. And people are also trying to come up with some model like dark energy, dark matter interaction. But we don't have a clear understanding of why this tension is happening. Because it tells us that there is something which we are missing about the universe. Basically because the observations of CMB is giving you one piece of information. The observations of the local measurement like supernova is giving us another piece of information. But if these two are not consistent with each other, that tells us that there is something really fundamental we don't understand. Possibly we don't understand many things, but this is something at least we can make an attempt to understand. And this is something which is going on for the last 2-3 years. People have been, if you should just type H0 tension in Google, it will give you thousands of pages. and in archive also there are lots of papers which people have been trying to work on to understand what is something which we are missing. There is something which we are missing, which is which seems to be fundamental, because H0 is a fundamental quantity in any cosmological observation. So again, I'll come back to it. So all this tells us that our perception about the universe is limited. So as I mentioned, so there is dark matter. We don't know whether dark matter is. People have been trying to propose modifications to dark matter, which is what is called the Mond theory. But Mond theory also has failed in various fronts, so it has other problems. Dark energy is a problem. We don't understand anything about it. It has very peculiar properties, like pressure is negative, which we have not even which we have not done in anything close to real life. So one possibility is to modify gravity at the largest possible scale, but it is complex because modifications to anything beyond GR turns out to have a lot of other problems. In the early universe, people have been trying to see whether it. So SUSY is one way of obtaining dark matter particles, but we don't know anything about. We have a lot of other problems with SUSY because there are other issues with SUSY from LHC. So string theory can help us understand the early universe, but there are other problems because there is a 2 years back there was a paper by Wafa and his collaborators. It says that it may be if there was inflation which could explain by string theory, then it cannot explain the same parameters cannot explain the accelerating epoch in the current universe. Loop quantum gravity tries to explain something, but we don't know anything much about it. It only explains again inflation. So all this basically tells us that we really have no understanding of the 95% component of the universe, which is dark matter and dark energy. So there are a lot of theories going around. It is good for the students because you can take a shot at some of these exciting problems, and you may even solve it. I think with that I'll stop, and I can take more questions. Yeah, now let me switch on my video. Yes, please.
Yes, sir.
So the thing is, many of these things, there can be two modifications to gravity. One is modification at high energy. One is modification at low energy. So the point of this thing is that at high energies you will have a different kind of modification. At low energies you will have a different kind of modification. These two modifications need not be the same. Okay. So the branch decay kind of modification actually is a modification at high energies, so-called. And what we are thinking about is the low energy modification, because these are going to happen at larger length scales, because we are talking about in gigaparsec scales. So those are going to be very, very different. So people are trying. So as I mentioned, for instance, let's just go back to the slide. So for instance, supersymmetry, string theory, loop quantum gravity, you can even modify gravity. They will all make changes because these are all modifications in the high energy regime. So they will make modifications in the high energy limit of the theory. But the dark energy is now happening in the low energy right now, right, where the energies are low. So you have to have modifications to it. So that is a different kind of modification. So these modifications need not be the same modification. There can be modifications in the high energies, definitely, but we don't know how to extrapolate those modifications to low energy modifications.
Sure.
Yeah, sure.
Can the theory of modified gravity lead to all the predictions that that general relativity gave?
Okay. So yeah. Yeah, so it depends on what the, so again, we are only, are you going to talk about modifications in the high energy regime or in the modifications to gravity in the low energy regime?
I was talking in overall, both regimes.
Okay, so so we know that we need a modifications to gravity in the high energy because, so for instance, black holes are singularities. Okay, so space-time singularities are bad because space-time singularities tells us that the physics, you cannot describe physics there. So automatically we know from theoretical ground that we have to modify gravity at high energy, and which is what loop quantum gravity string theory to certain extent supergravity also does that. Fine. Now there is no real reason to modify gravity in the low energy. In the sense there is no fundamental reason. Like for instance, low energy doesn't give you a black holes will tell you that in strong gravity regime you need to modify gravity because you don't. Singularities are bad. You don't like any singularity. Singularity is always bad for any theory because you cannot describe anything. So one thing which we have to do is so obviously there is a modifications in high energy is the strong gravity limit is necessary. The question which people are asking is that is it true that there is also changes even in the low gravity, in the sense like the largest possible scale, where the gravity is weak but still you need to have a modification. So the only possibility is that since this dark energy, as I mentioned, we need to have a negative pressure, and people are trying to say that okay, so that is maybe it looks very weird. Maybe we have to think about something else. Maybe modification to gravity is one possibility, but we don't know what is the correct modification. That is still a pressing question, which we don't know. There are lots of theories floating around. We don't know anything which one will be correct.
So, sir, it is possible to make changes in the high energy regime independent of making changes in the low energy.
Yeah. These are two independent. Yeah, they are completely independent. You don't have to worry about them. The corrections to the high energy limit and the corrections to low energy limit need not be the same. It need not have any dependence of each other because it's completely two different physics comes into picture, right? They need not be the same. It doesn't have dependence. That's what I meant.
Oh, okay. And so I've read somewhere that loop quantum gravity actually gave prediction that the two different frequencies of light will have few different speeds, and it was measured elsewise. So shouldn't we consider loop quantum gravity to be experimentally verified to be false?
So there is so the thing is what happens is that the dispersion relation. So many theories have been proposed, which gives you a modified dispersion relation. So what I mean by modified dispersion relation is that the photon, we know that the dispersion relation is p mu is equal to 0, which is nothing but omega is equal to k. Okay, and this is true for all energies, all frequencies. Now, so there are theories which say that the frequency dispersion, that is the dispersion relation, omega proportional to equal to k, is no more true. It might be different at high frequencies. It might have other contributions to it. So there are other people have been looking at it, but there is no real evidence. In the sense, there are lots of proposals, but most of it is it's not very. There is no real evidence that there is a dispersion relation there. Actually, the contrary, people have been trying to test it, but there is not. Even in, for instance, in what LIGO also tests a lot of these theories in their analysis, like test of GR and other things, but they don't seem to see anything significant till now.
So we can't certainly say anything about this.
No, we cannot rule out anything. See, the thing about physics is that we want to rule out things. If you cannot rule out, then there is nothing, not much fun. So the precise thing is we have to rule out models. We have to rule out things, and that is the problem. So if you cannot rule out, then it is a big problem.
Okay. Thank you very much.
Okay. There is we are easy talking about antiparticles and particles, antiparticles. If it is antiparticles, then we know that in the early universe, if I treat it as antiparticles, then I will just go ahead with this. If it is antiparticles, we know that in the early universe, both particles and antiparticles were produced, but we don't know a mechanism now. Still now, there is no clear mechanism which will say that why there are more particles than antiparticles. So that is what is referred to as baryogenesis, which tells you that why there are more particles, more baryons than antibaryons, and that is still an open question. We have no fundamental understanding of or fundamental theory which can tell you that this is the reason why there are more baryons over antibaryons. But black body interacts with light, no? That's where you say it's a black body radiation, right? Because it has a spectrum which gives that's how we see it. But in the case of dark matter, it doesn't interact with light. So that is your fundamental understanding. That is how we have defined dark matter to be. It doesn't interact, and that's where we don't see it in the observations. No. It is H0 is the Hubble constant for the current time. So the Hubble parameter. Other one is called the Hubble parameter, which is h of t, which is equal to a dot, which is the derivative of the scale factor a with respect to time divided by a of t, and that will keep changing. That is different at different epochs. So H0 is the value which we measure right now. What is the value of the Hubble parameter at the current epoch, which is referred to as H0. No, but we do see stars. It's not that we don't see. So we do see stars here and there, right? And we see them, and that's how we measure it. It's not, so what we do is that, okay, let's just go back to that slide. So we do see stars going around, okay, and we measure them. That's how we make the measurement, okay. But then we calculate it by saying that we make a rough approximation saying that this many number of stars should be present within this, because we see roughly how much is it, and then we make an estimate of how much should be the mass contained within that radius r, and that mass doesn't seem to be same as what we actually that seems to be much lower. That would have given you a much lower value compared to what you measured. So otherwise, how will you measure it? You measure it by looking at stars, and we see that the stars having a higher rotational velocity compared to what what the theory should have predicted, and hence there is a discrepancy. So since that mass which we have, which is lower than what we expected, should be much more than what we actually calculated. So that's where we are saying that. So those mass which we have calculated, maybe we have made a mistake in our calculation. There is other forms of matter which we don't know, and that form of matter has to be included. And since it doesn't interact with light, so we call it as dark. But it has all the properties like a matter. This is different than dark energy, because people get confused with dark matter and dark energy all the time. So the dark matter does not have pressure, P is equal to 0, but the dark energy has negative pressure.
So actually, I have a question. Sir, so I have read somewhere that bullet cluster has Mond theory has not able to justify the observations in bullet clusters. So
yeah, okay. So the thing is, so the Mond is basically what is called the modified Newtonian dynamics. It's a theory which tells you that the acceleration, that is F is equal to ma, is no more true, it has a parameter, it has an extra parameter, and depending on that parameter, it changes. So, but since it is a constant, it cannot keep changing. We cannot keep changing it for different galaxies. So people try to test the MOND proposal in the local cluster, then in the superclusters, then in the universe. So what they have found is that the variables which they use is different for different scenarios, and there is no fundamental reason why it should be different for these three scenarios. Because if it is the same modified Newtonian dynamics, you are modifying Newtonian dynamics, then why should that parameter should be different for different regimes? So they couldn't explain. So I didn't answer specifically to this, but this is to the bullet cluster. But this is the feature which they have seen it in MOND. So you can ask the same question: what should be the properties of dark matter? But so the properties of dark matter is very simple. It only has it has zero pressure. It has energy density. So of course there will be in the galaxies energy density may be diffuse or depending on what we have. So but it can explain with just basic features. It can explain few things, but not everything. So it is not that the dark matter solves most of the problems. Of course, there also you need to put a fudging factor here and there. But the problem with the MOND is that it can the parameters they use is very largely different. So then it becomes very problematic.
Okay, sir. Thank you. So are there any more questions?
Yeah, I have a question on redshift.
Sure.
Yeah, so when we use redshift to measure velocity, like we'll get a combined like effect of the expansion of the universe as well as the relative velocity of the body with respect to the Earth, right? So how would you like differentiate between them using the spectrum?
Can you repeat? I thought somebody else asked the same question before also. I think. So what I said is that so there are two components to the so the velocity has two components. What is called the velocity along the line of sight. There is a line of sight and the object which we are seeing. For instance, if it is a galaxy that is moving away from us, right? But then there is a local movement which is called which is also there. So there are two components to it. So that one is so what we do is that is basically going to be a spread, which actually introduces a spread into your spectrum. So in principle, your line width, when we get a signal, the line should have a Dirac delta function because it is one single frequency it is emitting. So that is how it emits, right? But then there is a line broadening which happens. The broadening can happen because of your experiment, your experiments are experimental errors which will happen because of the instrumental errors which can happen. But it also happens because of the peculiar velocities which is going around. The sense we are moving, as the sun is moving around the galaxy itself is moving. So all those things will also be present. But this whole thing is going to be true for all the spectrum which you are going to see. So that line broadening in some sense is going to be true for all the spectra which you are going to see. So we just subtract it out for all of it equally, and then we should be able to see what happens. I don't know whether that explains, but I don't think I have a picture. Okay, let's just go back to the picture. So what I'm telling you again is that if it emits a line, in principle it should be a Dirac delta function, just a blip, and that is what we should see. Now what we will see here is that we were not seeing this because we will see something which is spread around, which is like a Gaussian with a Gaussian wave packet kind of stuff. So that is because of the peculiar velocities which are local motion which is there. That's what I mentioned it here, but there will be local motion which will also be there, and that will account for this line broadening because we are moving around, everything is moving around. So there will be a line broadening which will be there. Even if you take a spectra from sun, for instance, you will see that there will be a line broadening which will be there, which will be little but not much. Okay, okay. But in this case, what will happen is that this line broadening is going to be true for all the spectra which you are going to see, not just in one line, but there will be in many lines. So we just subtract it out, and then we know what exactly happened. So there is a sophisticated data analysis one has to use, but it can be done. It is not that it is foolproof mechanism.
Okay, sir. Thank you.
There's a last question here. So, could we send a quantum entangled particle inside a black hole and study the particle's entangled partner to understand what happens beyond the horizon? Or does that particle stops communicating to its partner after it crosses the event horizon?
Can you tell the first question? So you have an entangled particle and it is thrown.
One of the partner is it is thrown inside the black hole, and the other particle remains outside. And we have to study.
Okay.
If we study the particle which is outside, are we able to get some idea about what's inside black hole?
Yeah, this has a lot of other things. So this is when we assume it's for a large black hole, for instance, a black hole of size of a solar mass, then the physics is very different. While if it is a very small black hole, okay, that is because of other physics which I don't want to get into it right now. So let us say the case you do this, and let us take the case you measure it. Now, what are we going to measure? We are going to measure. Let us take the spin. Let us take I have two electrons which are entangled. I'm throwing one electron into it. So we measure the spin of it. But by measuring the spin, we will not be able to say much about what has happened inside. So, but we need to do a lot of these measurements continuously. So I don't think so. Just by one or two measurements, we will be able to get much information about this.
Okay, sir.
I don't know whether that answers the question.
And there's another question. So I guess this will be the last question.
Sure.
Yeah. So it says that in the rotational velocity measurements, the calculated and the measured velocity go hand in hand till some period, and from the center, and after that it's the calculated and the measured velocities are different. So does that mean that dark matter is not found in the near the center of galaxy?
Okay, it's an interesting question. So basically, what it tells us is the following: we have accounted for most of the masses within the center. So as you know that the center of each galaxy, there is a huge black hole which is sitting around. Correct.
Yeah.
So basically that accounts for a lot of mass because it is 10⁶ solar mass. So basically, if you include that and the deviation will not be significantly large. So as you can see, you have a large black hole which is just sitting there 10⁶, and then you're adding small things, even small tiny changes. It's not going to account for it substantially. That's a simple way of looking at it. But how it happen is that, and it's also in a small region, so it is not going to account. It is not going to make much of a difference, even if you make if you don't include them. But as you keep going away from it, there is going to be a region of space which is empty, and that we have not accounted for because we don't know anything about it. So in that sense, it is basically that it is not that it is not present. It is just that even if you didn't account for it, it's not going to be significantly large error. See, you should also remember that we are making measurements here, sitting here, and looking at some galaxy. There is going to be errors which will be there. We try to minimize it, but it will be there. Okay. But most of the time, as many people laugh at it, for astronomer or for a cosmologist, pi is 3. It is not 3.14, blah, 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 blah. Okay. So you understand the error we are going to make there itself. So if I make it 3.14 to be 3, even that itself is very good enough to calculate most of the quantities. So we are not going to, it's not like in a condensed matter lab where you actually have to measure this to 5th decimal place. We are not going to do that because we'll never be able to do that. Okay. So, but even if you are not doing such a precise measurement, okay, but even though there is a significant error in this, even that itself is cannot account for this. That is even more glaring. That's what I'm trying to say. So compared to what we do in particle physics or in condensed matter experiments, the errors are going to be large here because we know it, okay, and we try to reduce them, okay. But still, the errors which we will get is significantly large, and we account for it. Even then, if you see such a glaring error, that basically means we have made a mistake. That basically means we have completely accounted. We have not accounted for it. Okay.
Okay, sir.
Okay.
So on behalf of everyone, I would like to thank you so much for this wonderful and interesting talk. We really appreciated that you have taken time out from your busy schedule for this talk. I would also like to thank the audience for participating in this Astro Talk. Thank you so much.
Thank you very much. Thanks. Bye. Is this guy left? Vinayak has left?
He's not on the. Yeah, he's not
He's
in
not
the.
there, right? He's not in the meeting. Oh, okay, that's fine. Okay then.